model for how the resistivity of damp soil varies with depth x from the surface is given by this equation, where h is the maximum depth and k and rho naught are other constants. What is the resistance of a vertical column of damp soil of cross-sectional area A and depth h? So immediately we should think, if we're dealing with a resistance and resistivity equation, we need to relate the two. So we would have R equals rho L over A. So that was for a resistor of constant cross-sectional area, A, length L, and resistivity rho. But you can immediately see the problem here is that the resistivity is varying with position or depth x. So how do we deal with this? Well, if you've tried past papers from the last few years, you'll see that Cambridge have been asking quite a few more questions dealing with quantities that seem to vary with either time or space, mainly space and position. And so the technique that you have to employ here is integration. But how can we think about how we get integration from this, or how we'd employ integration in this problem? Well, if we drew a bit of soil and then a column of depth h passing through here. So this is h. And then let's say this is the x-axis. We know that the resistivity depends on x. But the problem is that because the resistivity is varying, we can't just say rho times L over A, because which rho resistivity would we even use? So the trick, or the way to think about this, is that because we're used to equations where things are constant, if we were to break this cylinder or column down into very thin sections, so let's say I had a very thin section here of thickness dx, technically delta x, and then as the limit tends to 0, this becomes dx. But we'll worry about rigor in other times. So this is a very, very thin, so infinitesimally small section of this column. And the smaller it is, or the thinner it is, the more accurate it is to say that the resistivity is constant in this section. So we could say that if we started from the top, let's say we had an R naught there, then let's say there was some resistance from above that we dealt with. This is going to be 0, so I'm just putting this formally, that R naught is equal to 0. Any changes in resistance will be due to the extra gain in resistance due to these bits of soil. So dr, the change resistance, will be equal to, well, the resistivity at a point x, and then times the length of that section, dx, because it's meant to be infinitesimal. And then over, well, the cross-sectional area is the same, so we can just use this constant a. And then we can add up all these contributions. So we add, so s, or the integral summed, and then we add up. And then this is equal to all these changes. So that's why you'll see in a lot of integration you use d's, which mean changes, because they tell you how from a reference point. So we don't know what the initial resistance is. It's probably 0 because it's just some soil, and then let's say we take the air to have like 0 resistance, or it might not be. Again, it doesn't really matter here. But then what we're saying is the extra contribution just from the soil, the dr, the changes from whatever reference or base resistance we had, the dr, the change in R, delta R, is equal to these contributions from each bit of soil, rho times dx over A. And so if we actually carry through this integration, we have the integral from x is 0 all the way down to the maximum depth x is h. And then this is going to be, I'll take a rho naught from the resistivity and an over A here. And this will be 1 minus k x squared over h squared dx. If we integrate that, we get rho naught over A outside. We get x minus k x cubed over 3 h squared between h and 0. And x is 0. If we put it in, you can see it gets 0. So we just need to worry about that when x is h term. So we get rho naught over a, and then we get h minus, that's k over 3, h cubed over h squared is h. So this equals rho naught h over a. This is 1 minus k over 3. So let's see if that is in the same form as one of the answers. So rho naught h over a, 1 minus k over 3. Well, it actually is. It's answer E. So rho naught h over a, 1 minus k over 3. So just to get used to this technique, because this is something that Cambridge seem to be encouraging in the last few years, and it might be involved in the ESAT, because there seems to be fewer questions, or maybe not so much a focus on these types of questions. It might not come up, but it might as well, because we don't know enough from the practice papers that they've released. But integration is, well, calculus in general is essentially it pervades most of university physics. So if you don't get used to these techniques, you would then tend to struggle on university courses where these should become second nature to you. So if you keep practicing, getting used to what integration actually means and how to use it in a physics context, then you'll not only do well in these papers, but also in your university degree if you were to study physics or a STEM-based course. So I definitely encourage getting used to this technique, as you will see it in practically every year of your course. And you can just see how it marries the integration and calculus that you've learned in your maths with the physics topics that you've done, and how you deal with things when they're changing rather than just constant, because in most of nature things are rarely ever constant for long enough periods of time. So we have the answer is rho naught h over a, and then 1 minus k over 3, just to reiterate that this is the final answer. Hopefully that all made sense, but if there's any questions, please do let me know in the comments.